Hello there, Mr. Sutton bringing you the AB Calculus 6-2 homework solutions on separable differential equations. For this problem, we're given the differential equation dy over dt equals negative 2y, y is 1 when t is 0. Based on this, we want the value of t that gives us a y value of 1/2. So in order to figure this out, we're going to need an equation that has a t and a y in it. But we don't quite have that yet. We have a y, but we don't have a t. So what we're going to do here is essentially find the particular solution of this differential equation given this initial set of values here, and then we'll plug in 1/2 for y and solve for t. All right, so first off, in order to take the antiderivative here, I'm going to need to separate my variables because I have an output variable, this y here, in the differential equation. So I'll start by dividing both sides by y. So I've got dy over y equals, and now I'm going to multiply by dt to get that on the other side, so negative 2 dt. Taking my antiderivatives, this is going to be ln absolute value of y equals, this is going to be negative 2t plus c. Now I have to figure out the c value. Well, I know that y is 1 when t is 0, so I'm going to plug those in. I've got ln of absolute value of 1, which I don't really need the absolute value there, equals negative 2 times 0 plus c. Well, this just zeroes out, leaving us with c. ln of 1 is also 0, so c then must equal 0. All right, plugging everything in. Before we can plug 0 in here, let's figure out what we're doing with this absolute value. Since our initial y value is 1, that means in general y is positive, which means we no longer need the absolute value. We could just write a parentheses if we wanted, or since it's just a single thing, nothing at all. So I'm just going to write that as ln of y equals, we've still got negative 2t, and now the c value is 0, so I'm not going to bother writing that. At this point, you could go ahead and isolate y. There's not really a need, though, because we've already got an equation that has a t and a y in it. At this point, all you really have to do is plug in 1/2 for y and go from there. So I'm going to write ln of 1/2 equals negative 2t. Solving for t now, I'm going to divide by negative 2. And my answer then should be negative ln of 1/2 over 2. Should be, but if you look at the answer choices, that's none of the answers. So we have to do a little bit of log simplifying. Really, the only thing we can do here is we can move this negative inside the ln as a negative 1 exponent. If we have 1/2 to the negative 1, that's really 2. So I could write this as ln of 2 over 2, and then it would be positive, because again, I moved that negative 1 inside as an exponent. Do we have ln of 2 over 2 as an answer? We do. Choice C. For this next problem, this is kind of an oddball sort of problem. A student attempted to solve the differential equation dy over dx equals xy with these conditions. In which step did the first error appear? Okay, so going through here, it looks like in the very first step, they have separated their variables and then taken the antiderivative, and this was necessary because we have an output variable in there, so we have to move that to be with dy, and it looks like dx came over to be with the x. That's great. And yes, we need an antiderivative. So all of this is a good way to start the problem. Good job, mystery student. Next step would be to take the antiderivative and actually apply the correct rules. Well, the antiderivative of 1 over y is ln absolute value of y. Very good. X does become x squared over 2, or 1/2 x squared, and the student even remembered the plus c in case you were checking for that. Awesome sauce. Let's keep going. In this next step, what have they done? Well, it looks like here they have raised both sides, or raised e to both sides to get rid of the ln, because you have to isolate y at some point. At this point, honestly, we should have tried to resolve the y before leaving an absolute value. But even then, if you raise e to both sides, if you raise all this stuff as an exponent on e, then this plus c should still be in the exponent. It can't just kind of remain out here apart from the e term. Now, another thing you can do with the c value in the exponent, you can kind of split it off as like a times e to the c, and then call that a constant out in front of e, but they didn't even do that. So this is definitely the bad step, step 3, so choice B then. On this one, we're given this differential equation with 2y squared and told, let's see, y equals 1 when x is 1. When x is 2, what's the value of y? So this is one where you need to find the particular solution for all this information, plug in 2 for x, and then solve for y. Okay? So let's start by separating our variables. We need that on this one because we have an output variable, y, in our differential equation. So that needs to be with the dy. So we have dy over y squared, or I guess you could call this y to the negative 2, either of those with a dy, equals, now we have a 2 and a dx that comes up to join it. Antiderivative time, so this bumps up to a negative 1. Dividing by that, we have negative y to the negative 1 on the left side. On the right side, this becomes 2x plus c. Now we'll plug in the initial condition. Now be careful what you're plugging in. Y equals negative 1 was the initial condition, along with x equals 1. So this is going to be negative 1 to the negative 1. It's kind of crazy. So you can think of that as really just negative 1 over negative 1. And over here we have 2 times positive 1 plus c. All the stuff on the left is just 1. Subtracting 2 from that, we get c equaling negative 1. All right, time to plug everything back in. So I can rewrite this now as negative y to the negative 1 equals 2x minus 1. And at this point, I've got an equation that has a y and an x in it. I know that x equals 2. Now I just have to solve for y. So I'm going to go ahead and plug 2 in right away here. I could isolate y and then plug in 2, but why bother? Because if I isolate y first, then I have to mess around with moving variables, and I'd rather just have all constants. So I've got negative y to the negative 1 equals essentially 3. I can multiply both sides by negative 1 to get negative 3 over there, equaling y to the negative 1. And then to get y, I just have to flip both sides, the reciprocal. So y is going to equal negative 1/3, which is choice B. For this problem, we want the solution to the differential equation given here with this initial condition. So they're asking for the particular solution. They didn't say that word, but if they're giving you an initial condition, that's what they mean. And you'll notice there's no plus c's in any of these answers anyway. So first, we need to separate our variables because we have a y in our differential equation, or an output variable. So on the left side, I've got dy over y, or times y to the negative 1, either of those. And then I have on the right side, this equals negative 2x dx. Antiderivatives now. On the left, that's ln absolute value of y. On the right, this bumps up to a 2 for a power. Dividing by that, we have negative x squared plus c. Plugging in our initial condition, we had a y value of 4 that goes inside our ln. And over here, this equals negative 1 squared plus c. So we've got ln of 4, and this is still a negative 1 out here. That negative happens after the squaring. So adding that to the other side, then, I have a c value of ln of 4 plus 1, which is kind of weird, but hey, we'll work with it. Now plugging that back in, first let's resolve this absolute value situation. If our initial y value equals 4, that means in general this y value here is positive, which means I don't need the absolute value. I can just write ln of y with no absolute value, or at most a parentheses. On the right side, I still have negative x squared, and now I'm adding the c value of ln of 4 plus 1. Almost there. Still need to isolate y. To do that, I need to raise e to both sides of the equation. So that'll leave me with just y on the left side, cancels that ln. On the right side, I've got e to all of this stuff. And it looks like that's none of the answer choices. It's close to some of them, but they did something extra. So the key here is this ln inside the exponent. This ln could be kind of split off into its own e to the ln of 4 term, and e to the ln of 4 is really just 4. So we can rewrite this without the ln of 4 up here. We can actually just have a coefficient out in front here of 4. So this then becomes, I wrote this as e to the negative x squared plus 1 times e to the ln of 4, just like I said, and then this just becomes a 4 out in front, which leaves us with answer choice D. On this problem, we have a student attempting to solve the equation dy over dx equals xy cubed with these initial conditions. We want to know where the student messed up. So going through the different steps here, our first step on this should be to separate the variables, bring the y cubed under the dy, and multiply the dx to be on the right side. And it looks like the student did that. We have 1 over y cubed and x dx. So we separated variables correctly. And the student also correctly decided to start taking antiderivatives of both of those things. Okay? So over here, antiderivative of x is 1/2 x squared plus c, so that's good. Over here is the antiderivative of 1 over y cubed, ln absolute value of y cubed. Well, the ln of 1, or the integral of 1 over y cubed is the same as the integral of y to the -3 dy. And this just uses the reverse power rule. This bumps up to a -2. Dividing by that, we should end up with -1/2 y to the -2, not whatever we did over here. So this is the step where we messed up on that antiderivative. So choice B, step 2. For this problem, we're trying to come up with the solution to the differential equation given here with this initial condition. So let's start by seeing if we need to separate variables. Well, I see that I have a y here in my differential equation, an output variable. So that means I do need some separation. So I'll multiply y to be over here with the dy, and then I'll multiply the dx to be on the other side, so x squared dx. Now taking the antiderivative, we have 1/2 y to the second on the left. On the right, this bumps up to a 3, so that's going to be 1 over 3 x cubed plus c. Now let's use our initial condition. So this is going to be 1/2 -2 quantities squared equals 1/3 3 cubed plus c. On the left side here, this is going to be 1/2 of 4, which is 2. On the right side, this is 1/3 of 27, which is 9. 2 minus 9 is -7, so that's our c value for this one. Plugging that back in, we've got 1/2 y squared equals 1/3 x cubed minus 7, and there was nothing else to really finagle there, no absolute values or anything. So now we're going to solve for y. First, let's get rid of this 1/2 by multiplying everything by 2. So that's y squared equals 2/3 x cubed minus 14. Now I have to take the square root, and that means I'm going to have a plus or minus square root. But which branch should I pick, the positive or the negative? Looking at our initial condition, we see that we have an initial y value of -2, which means in general that y is going to have to be negative for this branch. So that means when I take my square root, I have to write y equals negative square root of all this stuff, which ends up giving me answer choice E. For this problem, we have this differentiable f function with the point 3, 1/4 on it, and a slope given by this differential equation here. First part of the problem, they want the second derivative, and then they want to evaluate that at the point 3, 1/4. So to find our second derivative, we have to take the derivative of dy over dx, and for that we're going to need the product rule, u prime v plus uv prime. To help organize the information, I'm going to use my box and ribbon, but I am eventually going to want to plug things back in over here because I need to at some point evaluate this point and also tell them what d squared y over dx squared is. So I've got y squared and 6 minus 2x. The derivative of y squared is going to be 2y dy over dx. We're differentiating implicitly because in general we're taking the derivative with respect to x on this problem because we already were taking the derivative with respect to x here, and this dx squared is adding another derivative with respect to x. So we're going to need to have that tail in there. Now at some point I'm also going to have to go back and plug in the stuff that dy over dx equals for this expression right here. But I'll do that in just a minute. My other derivative here of 6 minus 2x is going to be -2. All right, so let me just label these as u, v, u prime, and v prime, just to be clear and take no chances. Plugging all those back in now, I'm starting with u prime and using my ribbon. So I've got 2y times dy over dx, which is really y squared times 6x, or 6 minus 2x. So all of this stuff right here is just this dy over dx from my box. And all that's getting multiplied by this 6 minus 2x over here. This is the v. Now, that was kind of annoying and nasty, but going the other way on the ribbon is a lot nicer. This is just going to be minus 2y squared. And I'm going to go ahead and clean this up a little bit here. So 2y times y squared, that's 2y to the third, and these two 6 minus 2x's can get moved together to be a 6 minus 2x quantity squared. And I still have this minus 2y squared kicking around out there. All right, so this is our second derivative. We've written it out for them. This up here would have been enough. Honestly, I think this wouldn't have quite been enough, even labeling the box, because you needed to actually plug stuff in for the dy over dx, but definitely here we're good. Anyway, let's plug in the point 3, 1/4, and you can do that in the box or down here. I've already gone to the trouble to simplify all this, though, so I'm going to plug it in down here. So evaluating now our second derivative at 3, 1/4, that's going to be 2 times 1/4 cubed times 6 minus 2 times 3 quantity squared minus 2 times 1/4 squared. All right, this looks like a big mess, but if you look closely, you'll see here we have a 6 minus 6 in here, which is just 0. So this entire first term is actually getting zeroed out. Hopefully you spotted that fast. And then so it's really just the second term here. We have negative 2 times 1 over 16, which is really negative 1/8 if you wanted to simplify it. You actually didn't need to simplify it, but hey, why not? Because I'm not actually taking the AP test right now. For the next problem part here, they want us to solve this differential equation with this initial condition. So they want the particular solution, so figure out what the plus c is and make any other adjustments. For this one, we're going to need separation of variables because we have an output variable, y, in our differential equation. So I'm going to move y over to the left side by dividing. So I'm going to write dy over y squared, or you could write y to the negative 2y squared. I actually like it better that way because then I can take my antiderivative a little easier. On the right side, we have 6 minus 2x quantity times dx. It's important to keep that parentheses there. We don't want just 6 minus 2x dx with no parentheses, because that wouldn't be the same thing. All right, antiderivatives. On the left side, this bumps up to a negative 1. Dividing by that, we've got negative y to the negative 1. On the right side, we've actually got a few terms to take the antiderivative of. 6 becomes 6x. This negative 2x is going to be negative x squared if we bump that exponent up to 2 and divide. And don't forget your plus c. Moving on then, we're going to plug in our initial point. So we have a y value of 1/4 that's going in over here. So I have negative 1/4 to the negative 1. And over here I've got 6 times 3 minus 3 squared plus c. On the left side, well, this is really 4 if you take the reciprocal, and then it's negative 4. Over here on the right side, this is 18 minus 9, which is 9. So we have negative 4 minus the 9 that's already over here, which gives us negative 13 for our c value. It's kind of an interesting c value. Usually it's like 1 or 0, but hey, something else now. Let's plug that back in at this point. So I'm going to rewrite this whole general solution, but with a negative 13 for that c value. Only thing left to do is isolate y. So next step I'm going to take is to multiply both sides by negative 1 to get it positive y to the negative 1 on the left. So that'll be a positive x squared minus 6x plus 13 over on the right. And then to get rid of this negative 1, we're just going to raise both sides to the negative 1. So take the reciprocal, which gives me y equals 1 over all that stuff. For this problem, we're going to be using this stem here where we have solutions to the differential equation also satisfy this second derivative. So they basically just took the derivative for us. That was nice of them. And we've got some particular solution, this y equals f of x, with an initial condition of f of 1 equals 2, based off of all this stuff up here. First part of the problem, they want the equation of the tangent line for f at x equals 1. So in general, I'm going to use my L of x formula. L of x equals f of a plus f prime of a times x minus a. Now, a in this case is 1. That's our launching off point. So I have then L of x equals f of 1 plus f prime of 1 times x minus 1. So really all I have to do to finish this part of the problem is figure out f of 1, which they already gave me here, and f prime of 1, which I can find using this differential equation. So f prime of 1, that's just going to be what happens when you plug 1 in up here for x. But now you also have to plug in something for y. You have to plug in the value of y when x is 1. So I'm plugging 1 in for x, and then I'm going to be plugging in 2 for y. So this is going to be 1 times 2 cubed, which is 8. So plugging that in over here, we have L of x equals 2 for f of 1, plus 8 for f prime of 1, times parentheses x minus 1. For this next problem part, they want us to use our tangent line equation from part A to approximate f of 1.1, and then there's some other stuff they want. But let's do this first. So I'm going to write f of 1.1 is approximately equal to L of 1.1. And L, remember, that was 2 plus 8 times x minus 1. So I'm going to write 2 plus 8 times 1.1 minus 1 now, using our L formula from part A. And we actually could stop here, but if you want to simplify it, this is going to end up being, let's see here, 2 plus, this is 0.8, so 2.8. So now let's read the rest of the question here. Given that f of x is greater than 0 for 1 to 1.1, is the approximation for f of 1.1, this 2.8, greater than or less than f of 1.1? Explain your reasoning. So we're essentially asking, did we over or underestimate using our approximation? And with linear approximation, the way we figure that out is by looking at the concavity of the curve over the interval from our starting point to our estimation point. So the concavity then is given by this second derivative equation up here, d squared y over dx squared equals this craziness with y cubed. So we're trying to figure out, is this thing negative, positive, or both on the interval from 1 to 1.1? And they actually gave us a major hint here. They said that f of x was greater than 0 on the interval we care about. Well, if that y is greater than 0, f of x, same thing, well, that means that this y in here is guaranteed to be positive, as is this y over here. So that's not going to affect anything. What it's really going to come down to then is the other stuff here. Now, this x is being squared. So that means that negative or positive, whatever x is, we're guaranteed to get a positive here. And over here, we are adding, which if you're starting with a positive and just adding, it's going to stay positive. So given that y is greater than 0, this thing has no choice but to be positive on the interval from 1 to 1.1. Therefore, that means that y is concave up on this interval, which means since you're concave up, a line is going to go under that essentially. So this 2.8 is going to be less than the true value of f of 1.1. For this problem part, they want the particular solution for f of x with this condition of f of 1 equals 2. So looking at my differential equation, I see that I have a y, an output variable in the differential equation. That means I'm going to have to separate variables before integrating. So I'm going to do dy over y cubed, or y to the negative 3 times dy, same thing. And then I'll multiply to get the dx over to the other side with an x that happens to be over there. Antiderivatives now. This over here bumps up to an exponent of negative 2. Dividing by that, we have negative 1/2 y to the negative 2. Over on the right side, this will be 1/2 x squared plus c. Now we have to plug in our initial condition. So we've got negative 1/2 of 2 to the negative 2 on the left side. So that's essentially negative 1 over 2 times 2 squared. And then on the right side, this is 1/2 times 1 squared plus c. On the left side, this is, let's see, negative 1 over 8. On the right side, we just have 1/2 plus c. So I essentially have to subtract 1/2 from negative 1/8. That's negative 1/8 minus 4/8, so negative 5/8 when all the dust settles for my c value. Plugging that back in, I've got all of this stuff, and instead of plus c, I've got a minus 5/8 over there. But not out of the woods yet. I still have to isolate the y value here. And there's a lot of ways to go at this point. Just to do this as cleanly as possible, I'm going to get rid of all the fractions by multiplying by 8. Didn't really have to do this. Maybe a little overkill, but I'm going to really neaten this thing up. So that gives me negative 4 y to the negative 2 on the left, equals 4x squared minus 5. So no more fractions. Next, I'm going to go ahead and divide both sides by 4. And while I'm at it, I'll reverse these. So I'm writing 5 minus 4x squared, because why not? So all of that over 4. And now if y to the negative 2 equals that, well, I don't really like that negative exponent, so I'm going to reciprocal both sides. So I have y squared equals this stuff upside down, 4 over 5 minus 4x squared. And then finally, I have to take the square root. But before I do this, I have to figure out, am I taking the positive or the negative branch of the square root? So looking at my initial condition, I see my initial y value is 2, which means in general, y has to be positive. So that means when I square root this, I have y equals positive square root of all that stuff.